So when we focus on energy, we will focus in this class on both kinetic energy and potential energy, but potential energy in the form of chemical energy. That has to do with breaking bonds and forming bonds in compounds, in new compounds, of course, forming the new bonds and breaking bonds in the older compounds. Well, let's talk about the units of energy. The unit of energy is joule. And it's equal to the kilograms meter squared per second squared. That's what you get when you plug in numbers into either one of these equations, whether it's some potential energy or kinetic energy. The joule is not a lot of energy. We also need to introduce another unit that we use for heat, and that is the calorie. And you need to know, and it's CAL if it's just calorie. Make this C lowercase. And it's equal to 4.184 joules. Now, joules is not a lot of energy, so we usually express it in kilojoules. So you'll see that a lot. So kilojoules, like if we have 1 kilojoule, that would be 10 to the third joules, or 1,000. Same thing with calories, is that we will express things in kcal, which is 1,000 calories. Now, even kcal is sometimes written with uppercase or a capital CAL, which also means 1,000 calories. This is nutritional calorie. That's the calorie that is found on any nutritional profile that you see on any food item. So keep those in mind. Now let's talk about important definitions, because when we talk about heat in this chapter and energy changes, we need to understand our terms. We are talking about relative here. Here, things are relative. So let's begin. We have something called the universe, and that is comprised of everything in this realm we live in. Earth, the galaxies, the air you breathe in, you, etc. So that's the universe. But then, more in particular, we need to pay attention to what we call the system, which is the part we're interested in studying. And usually this is a chemical reaction, unless, of course, we talk about physical changes or physical properties. The chemical mixture and the surroundings, and that's everything else in which the system can exchange energy with. So imagine you have a flask, and this flask has a reaction mixture. And this flask is being, let's say, heated on a, let's say, a hot plate. And of course, there's air in the surrounding, in the vicinity, with its own temperature, all of that stuff. Your system would be this mixture. That's the system. So it's the solution, the chemical solution, reaction solution, or mixture, whatever it is. And of course, everything else is the surroundings. So you need to keep that in mind, because we will study now energy, the energy exchange between both the system and the surroundings. So even you would be considered part of the surroundings. So now let's move on to work and heat. A few things about work and heat. We will mainly focus on heat, but just a very simple thing to talk about in terms of work. So work is energy used to cause an object to move against a force. As simple as lifting a book. So you have a book here. If you lift this book against the force of gravity, this is, let's say, the floor. Well, you are doing work on the surrounding. You are doing work on the system. In this case, you're moving it against the force of gravity. So again, moving it, the book, against the force of gravity. Pushing something. But remember, it has to involve a distance. It has to involve a distance. So if you can't push something, and like if you push against the wall, then there's no work because there's no distance. But the more important one is heat. Heat is the exchange of thermal energy, as you saw in the kinetic energy portion between the system and the surroundings caused by a temperature difference. So usually also defined as an energy transferred from a hotter object to a colder object. So very simple. There has to be a temperature difference. If two objects have the same temperature, then they cannot exchange energy because one has an equal amount of energy to the other. So they have to be at a different temperature. So let's say you have an object at 21 degrees Celsius and you have an object at 86 degrees Celsius. You know this one has the higher temperature and this one has the lower temperature. So therefore, there can be an exchange, of course, from the one with the higher temperature to the lower temperature. But you cannot have an exchange when they are equal in temperature. So that's an example. So let's give you an everyday example. You have an ice cube, and you place this on your hand. Pardon my drawing here. On your palm of your hand. This ice, I don't know why I said cube here. Cable, ice cable. Okay, it's ice cube. So you know that there's going to be an exchange of heat. So you have high temperature on your hand, low temperature on the ice cube. So therefore, there's going to be energy moving from your hand to the ice cube. Perceptually, it feels different because it feels like something is leaving your body, or like the cold getting into your body, but it's actually your hands that are losing energy in the form of heat, of course, to the ice cube, which is causing the ice cube to melt. So that's an idea, a simple way of showing and representing heat. There has to be temperature change. So first law of thermodynamics, very quickly, make sure you understand what it says, is that energy can neither be created nor destroyed. Any energy lost by the system must be gained by the surroundings. So energy cannot just disappear out of this universe. Okay, it's conserved. That's what it is. Energy is conserved. But it is transferred, right, from one system to the other, to, let's say, the surroundings. Kind of like when you talked about redox reactions, when the electrons have to go from somewhere, from one compound to another compound. They can't just go and disappear. They have to go somewhere. Some technical definitions here is that you have, since any object can have both kinetic and potential energies because it has different components. Like if you have a waterfall, It has potential energy at the top of the fall, the peak of the fall, and then it has kinetic energy as those water molecules are moving. So you have the sum of all of these kinetic and potential energy of the components of this sim called U. It's called, the symbol is U or E. That's internal energy. We're going to call it E. So here is a very important concept to remember, is that the internal energy of the system in magnitude changes in magnitude as heat is added or removed from the system, or as work is done on it or by it. Okay, so what does that all mean? Here is what you need to remember. When heat is added to the system or when work is done on the system, the change in energy increases. It becomes positive. I mean, think about it. If you add heat to the system, it gained heat, right? So heat is gained. Therefore, the change is going to be positive. Or if something is doing work on it, it's not doing work, something is doing work on it. So think about it. If you put in work here, over here, look here, then that's going to be positive. If you put in energy in terms of heat, that's going to be also positive. Now, the opposite is true. If work is done by the system or heat is removed from the system, then the change will be negative. So what does that all mean? It's important that for us to study this because we need to be able to understand what this means. So let's actually give you an example of how can you have something called negative energy or negative heat? Like, how is that possible? Well, the sign just tells you what you need to know. So let's actually look at what delta E means. So think about delta. When you talk about the word or the symbol delta E, delta means what? The difference in energy. Or any difference. Anytime you see delta, it means difference in energy. So doesn't that mean that you subtracted things? Yes. So delta E means E final minus E initial. We're going to call them EF and EI. So think about it. If you get a negative, this can only mean that the E final, EF, is smaller than E initial. If you don't see it, just let's plug in some numbers. So if I have a 5 for a 5 joules for E final, and I have 10 joules for E initial, you know that E final is smaller than E initial. 5 is smaller than 10. I don't have to show you that. So what's 5 minus 10? That would be a negative 5. Look at the sign right there, a negative 5. So that means energy is lost, okay, by the system. Lost by the system. So we say if we have a negative, is lost by the system. Since almost always we will talk about things in relation to the system, not the surroundings. So lost by the system where? Where do they go? To the surroundings. Now think about it. If you have a delta E of positive, then the opposite is true. You have E final now greater than E initial. Just reverse the numbers. 10 joules minus 5 joules, that gives you plus 5. Once again, positive now means energy is gained. By the system. Whether it's in the form of work or heat. So keep that in mind. These changes are going to have an influence on the sign of the energy. Now, to wrap things up before we go on to the next video, we need to talk about two processes here. And these two processes are exothermic and endothermic. Okay, not sure why they weren't moved. So exothermic is a process in which heat, so if we just focus on heat, heat out, that's what exo means. Exo means heat out. The process in which heat is released from the system to the surroundings. So if we focus only on heat, if the system releases heat, that's called an exothermic process, an exothermic process. If you have endothermic, that's a process in which heat is absorbed by the system from the surroundings. So it's the opposite, and look at these two representations. So this one is heat in. Very well. So if we look at an example of where heat is released. So if you, let's say, have something you burn, let's say, a hydrocarbon, right? So burning a hydrocarbon. Releases heat, and the reaction, let's say in this case, the flask becomes hotter or warmer. Then that means that this reaction released heat. And if you notice here, Q is minus. Whereas if you have endothermic, if you have something as simple as the reaction flask becomes cooler, then that means that, again, this system actually absorbed energy from the surroundings, and then Q would be a positive or a positive value. So anything that you have to put in energy in is endothermic. So this could be like evaporating something. You're putting the energy in to evaporate it. But an exothermic process is the one that actually releases heat after the reaction took place.